Hello. Another video on the lead bath method. This time though, we started with 10.5 kilograms of scrap. The scrap consisted of 240 grams of Soviet ICs, 730 grams of DIP ceramic chips, 2.1 kilograms of transistors, and 7.5 kilograms of ceramic CPUs. Our first step was melting the lead into a working molten pool. Once the lead bath was up to temperature, we began adding the scrap. We stirred thoroughly, making sure all transistors were wetted by the molten lead. Once the material was submerged, we replaced the furnace lid for a minute to recover the heat lost during the addition of the cold scrap. After the melt returned to a dull red glow, we gave the transistors a final stir and started scooping the spent casings out with a perforated ladle. The scooping process is a critical step that requires a steady hand. It is essential to strain every possible drop of lead from the empty casings back into the melt. We give the ladle a thorough shake to ensure minimal drag-out. We process the rest of the scrap in a similar manner, including the bulk of the ceramic processors. With each charge, we also added a small amount of flour to reduce any litharge that might have formed back into metallic lead. As the flour burns, the carbon reacts with the lead oxide, effectively recycling the lead back into the pool. By keeping the lead in its liquid metallic form, we ensure maximum contact with the incoming scrap and a much cleaner separation when it comes time to scoop out the waste. Now that all the scrap has been stripped of its precious metal content, it's time to introduce the silver. For this run, We're using a mix of scrap silver jewelry and silver contact points. Adding silver at this stage serves several vital functions in the refining process. Firstly, the silver acts as an additional collector, aiding the scorification and cupellation stages, acting as a protective carrier for the gold as we begin to drive off the lead. More importantly, this is the inquartation phase. We need to ensure the gold content of the final precious metal doré is low enough, typically a 3:1 ratio, to allow for effective parting in nitric acid later on. If the gold concentration is too high, the acid won't be able to penetrate the alloy to dissolve the silver. At the same time, we're refining this scrap silver alongside our recovered gold, making for a highly efficient run. We're preheating the ingot mold to drive off every trace of moisture. Skipping this step is a recipe for disaster. Even a microscopic amount of trapped humidity can flash boil into steam, causing a violent explosion of molten metal. We ensure the iron is bone dry and has enough thermal mass so it doesn't shock the alloy. Once the mold is sufficiently heated, the risk of a steam explosion is mitigated, and we can proceed with confidence. With the mold preheated, we begin the pour. The liquid doré alloy flows smoothly, consolidating our recovered gold and silver into a single manageable cake. This cake represents the successful transition from a pile of electronic scrap to a concentrated precious metal alloy, ready for the next stages of refining. Preparation for the scorification step begins with the equipment. We are shaping a custom scorification tray by hammering a stainless steel sheet over an anvil. This shallow, dish-like profile is intentional. We need a large surface area to encourage maximum oxygen contact once the metal is back under the heat. Unlike a deep crucible, this open tray allows the lead to spread out, which is essential for the oxidation process. By fabricating our own vessel from stainless steel, we can ensure the tray is perfectly sized and robust enough to withstand the corrosive nature of the molten litharge, while providing a stable platform for the final concentration. All the precious metals from 10.5 kilograms of material now concentrated into a single metallic mass, ready for the fire. The fire is burning already, with forced air blowing under the lit kindles to build a powerful, oxygen-rich base. To sustain the intense heat needed for scorification, we are adding coal coke. With the air-fed coke fire established, we've created the perfect environment to melt our doré cake and begin the aggressive oxidation of the lead. The wide, open profile of the tray is now ready to do its job. Here we are adding sodium hydroxide flakes. At these temperatures, the caustic soda becomes a highly reactive liquid flux. This addition serves a dual purpose. It reacts with any remaining ceramic residues or surface oxides, dragging them into a fluid slag that floats above our precious metal pool. More importantly, it helps to clean the surface of the melt, ensuring that once the lead is fully liquid, it can interact freely with the atmosphere for the scorification process. As the tray reaches temperature, the lead will liquefy once more, spreading out to begin the scorification process. We are working with highly corrosive materials and toxic heavy metals. Full PPE is non-negotiable. The fumes from the molten lead and the reaction of the caustic soda are extremely hazardous. Never attempt this without professional-grade ventilation and respiratory protection. We ensure that once the lead is fully liquid, it can interact freely with the atmosphere for the scorification process ahead. With the melt fully up to temperature, the next phase of the process begins. We redirected the forced air from the bottom of the furnace and began blowing air directly over the pool of molten metal. This shift is fundamental. We are no longer just heating the alloy. We are now using oxygen as a reactant. As the air passes over the liquid surface, it reacts with the lead to form litharge. This steady stream of oxygen accelerates the oxidation process, causing the lead to burn off while our precious metals, the gold and silver, remain protected within the melt. The sodium hydroxide flux we added earlier keeps the surface clear, allowing this reaction to proceed without being stifled by a thick crust of dross. By controlling the airflow and the temperature, we are systematically reducing the volume of our collector. In a batch of this scale, the steady removal of lead is a game of patience and precision, bringing us closer to the final concentrated doré bead. As the oxidation continued, the volume of the melt steadily decreased. When the size of the molten pool was reduced to approximately 1/10 of its original volume, we stopped the airflow and removed the tray from the heat. We then left the concentrate to cool and solidify. The large cake we started with has been refined down to a dense button, significantly enriched and nearly ready for the final cupellation. Once the tray had completely cooled, the lead oxide had formed a solid, brittle crust around our enriched doré. Allowing it to solidify now gives us a chance to separate the metal from the litharge and to clean the stainless steel tray, getting it ready for the cupellation step. Mechanical separation at this stage is straightforward. The litharge is quite brittle and breaks away easily, leaving us with a concentrated precious metal alloy. Now, with the tray in the furnace, we raise the temperature to remelt the metal. We need to bring the alloy back into a fully fluid state to begin the final cupellation. Again, we added the flux. Because the lead content is now much lower, the melting point of the alloy has shifted, requiring a steady, intense heat to ensure a clean start. As the button liquefies, the surface becomes a bright, shimmering pool. We are now entering the final stretch. Now the metal has melted and we are blowing air over it. This final stream of oxygen is working to drive off the remaining impurities. The last bit of the lead is being oxidized to litharge, which forms a thin, glassy layer on the edges of the molten pool. To keep the reaction moving, we pulled the litharge away with the help of a metal rod. By manually clearing the surface, we ensure that the air stays in direct contact with the metallic lead, preventing the oxide layer from blanketing the melt. The final streaks of oxides are running on the surface of the molten metal just before closing. These moving patterns, often called the play of colors, are the very last traces of lead being forced out of the alloy. And there it is. The surface clears instantly as the last of the litharge is driven off. This is the brightening or flash of the bead. The lead is gone, leaving behind a high-purity doré alloy of gold and silver. results are in. The silver doré is on the scales, showing a final weight of 279 grams. The next step is to break this alloy apart. To dissolve the silver and reveal the gold, we covered the doré metal with 50% distilled water and 50% nitric acid. To accelerate the process, we heated the beaker. As the temperature rises, the nitric acid begins to aggressively attack the silver. After more than 3 hours of boiling, first in dilute and then in concentrated nitric acid, we are almost done. As you can see, the last pieces of silver are dissolving away. What remains at the bottom of the beaker is the concentrated gold from our 10.5 kilogram run. With the dissolution complete, we now have to make sure we've removed every last drop of silver nitrate from our gold mud. For this purpose, we boiled the gold several times in distilled water, followed by a final boil in concentrated nitric acid to hunt down any microscopic traces of silver. We then returned to distilled water to thoroughly flush out the nitric acid. As an extra insurance policy, we performed a couple of boils in concentrated hydrochloric acid. This step ensures that any stubborn base metals or iron are stripped away. Finally, we finished with several boils in distilled water to remove every trace of chlorides. With the purification complete, we have transferred the damp gold into the melting dish and sprinkled some borax over it. We start with a soft flame to drive off the moisture. This is the moment where the gold mud finally returns to its true metallic form. While the metal is still glowing with residual heat, we picked it up with tweezers. The visible dark green solidified borax glass left inside the crucible indicates that the flux has successfully scavenged the final traces of impurities. To give the gold its final luster, we boiled the button in citric acid. This step is a gentle pickle designed to remove any excess borax that might be clinging to the surface. And this is it. 67 grams of gold from 10.5 kilograms of electronic scrap, sitting in the palm of my hand. All in all, a successful day, despite the lopsided timeline. It's funny to think that dissolving the doré took more time than the entire initial stripping and recovery process combined. However, when you're chasing 99.6% purity, you can't rush the science, or maybe I should have started with concentrated nitric acid. Either way, the gold is on the scales, and for me, that's a job well done. We've taken 10.5 kilograms of industrial waste and turned it into a solid, high-purity asset. If you found this technical breakdown useful, I'd appreciate it if you'd like, comment, and subscribe. It really helps the channel. Thanks for following the process on this run. And remember, to me, you're worth more than gold.